So we're going to talk about machine learning predictions, how you can improve them using connected features, so features based on relationships and how things are connected. This is a pretty short time frame. We have about 20 minutes. I think this abuts a break, so you can always find me later if we don't have time for questions. I'll also be downstairs in the booth later tonight and tomorrow as well. We're going to look at Y graphs to help with your predictions. We're going to look at connected features, and in particular, link prediction, and also a Neo4j plus Spark workflow. And everything that I am going to talk about is mostly covered in Chapter 8 of the book that was released last week from O'Reilly called Graph Algorithms with practical examples in Spark and Neo4j. I'll show this again at the end so you know where you can get the book and download that. So quick question to the audience. Can you guys guess what is predictive in common between these two scenarios? We're trying to predict whether someone might smoke, and we're trying to predict whether someone might vote in the future. Anybody want to dare to guess? Considering I'm from a graph company, what's actually predictive in common here is the relationships. So, and these two scenarios are actually based on research that was in this book. There's actually several books about connections. But what we find when we look at this, when we look at relationships, is they're often the strongest predictors of behavior. So if you think about trying to estimate whether an individual might be a smoker, it's actually more predictive that their friends either do or don't smoke than some demographic income level where they might happen to live. Well, it's not too hard to believe. That kind of makes sense. The book also covers the voting scenario as well. So I like that scenario because they find it's predictive whether someone's going to vote in the future, not just of whether their friends say they're going to vote, but whether their friends' friends that they don't know say they're going to vote. And that's really interesting. That kind of shows the power of networks and people we don't even know that influence our behavior. So we know relationships are predictive, and graphs are a way to represent relationships and networks. So how many are already using graphs or familiar with graphs? Quite a few, love it. If you're not really familiar with graphs, graphs are all around us. They basically are a mathematical representation of things that are connected. We call them nodes for entities, relationships for links or edges, but it could be anything from a traffic or a logistics or a transportation graph to a graph of brain functions or a graph of products, or a graph of how people vote. So graphs are really all around us, and we know they're a way to look at relationships, and we know that relationships are very powerful for prediction. So there's a lot of use cases for graphs in general for data science, financial crime detection, drug detection, or drug repurposing. Those are some really common ones. Recommendations, if you can understand what people around you are doing, it's easier to predict what that person may do again. Churn prediction is a really fun one because trying to predict whether a customer will leave your subscription service and whether they'll pull other people to leave your subscription service is a very relational networked type of problem. So lots of use cases. If you're interested in graph-enhanced machine learning overall, there's a talk just shortly after this one at 4:30, room 202, where my colleagues will talk about all the different ways that graphs can enhance machine learning in general. What we're going to talk about is up and to the right, that's connected features, and how that can help with more context for accuracy, precision, and recall. So if we think about connected features and what that means, that's basically a feature that's somehow representative of the relationships inherent to what you're trying to predict. Now, features for machine learning and connected features for machine learning, you can think there's three-ish ways that they can really help with precision and machine learning predictions. First is feature extraction. So that's really just about how do I change the data that I already have that's naturally networked, because that's how most of our data comes, is it is actually already has the relationships there. How do I change that into a shape that's usable in my machine learning pipeline? And that could be really something as simple as saying, hey, I've got this graph, and I really just want to do my machine learning on the most connected nodes. So perhaps I do a strongly connected components algorithm, look for those communities that are more dense, and then I pull that out, I use that as my filter, and I run that through my machine learning. So much faster to do that than to use a table with lots of indexes and try to parse your data down manually. So that's a simple way you can just gain some efficiencies there. Another way which you can use graph is feature engineering. This is my favorite, one of my favorite topics. So using feature engineering is basically, how do I process the data I have and actually create new features that are more predictive because they're related to relationships than I may have already had. And the graph algorithms that you could use for this would be things like connectivity, community detection, you would expect that, but also things like influence. Maybe I want to take a look at and score which nodes in my network are the most influential, put scores on that, and then use that and extract that into a machine learning pipeline and kind of go down that route. The other area to look at is feature selection. So we know how to get the data out. We've talked about creating features, but let's say I have 100, 500 features now. How do I make sure that I use the most important features for my model? So we all kind of probably dealt with overfitting and creating models that are too particular to just our data or just the data set we were training on. You can actually use an algorithm like PageRank. And I assume everybody know what PageRank is, familiar with that? All right, got lots of nods, great. So you can use actually PageRank. There's a couple papers out there where they use PageRank to say which features are most influential in my model and basically use that to get rid of or reduce the features that aren't influential and reduce overfitting. So several ways that you can use graph algorithms to help improve your machine learning. One of the things that when we think about these is, as I said in the beginning, relationships are extremely predictive, and so many of us are not using them in our data. So we take the data we have, we put it in these nice little tables, we pump that information into our machine learning pipeline, and we've basically either abstracted or eliminated the relationships which are the most influential or the most predictive elements of our data to begin with, especially if we're trying to predict behavior. So the message, I guess in general, of this session would be, don't throw away your predictive information that's already in your data. Use it. It's almost like getting more data for free. And you can do that without having to change your entire machine learning pipeline. You can do that to just improve the features you have and continue on with the pipeline you had. In particular, link prediction. So there's an entire chapter in the book I mentioned on enhancing machine learning, in particular link prediction. And that's an interesting one right now because there's a lot of interest in predicting what may be related in the future. So when you think about link prediction, it's usually about trying to infer that somebody may take an action or a relationship may form in the future, or it's about trying to find the holes in your data, unobserved facts. So you might look at something, and there's an interesting research paper about using this with criminal networks where they believed, looking at the network, they actually should have had some relationships between these different crime syndicates, but they weren't there. So using link prediction, they can then target those areas to look for relationships they don't yet have in their data. So those are kind of the basics of what link prediction is. There's an example that I really just am, it's really kind of exciting. Het.io is an organization that has decades of biomedical information in a knowledge graph, so a different type of graph based on trying to link information. And they use link prediction to help predict new uses for drugs, so drug repurposing, using a graph structure and the topology to create their features. And so if you get a chance, if you go to het.io, they actually have a browser that you can actually, if you're in the medical industry at all, they have a browser where you can browse different diseases, different genes, and do some of the analysis, use some of the analysis they have. But this example right here, we're looking at a multiple sclerosis disease. We're looking at a gene, IRF1. And what they've done here is predict there might be a link here. It's not a direct link. But what they're able to do using link prediction is to follow the secondary, the tertiary paths and try to estimate that this gene may actually have some influence on multiple sclerosis. Very interesting, but it also means that the drugs that use or target IFR1 might also be a good target for multiple sclerosis. So it's a way they can help bring drugs that are already out there and tested faster to the market and use them for alternative uses. So that's just one example that's kind of exciting. As far as link prediction goes, there's a couple different ways you can do link prediction, usually two main different ways people do that, especially with graph data. They use either algorithm measures, and those would be basically you have some algorithms that you think are going to show some predictive information, and I'm going to set a threshold value. If I get a threshold value above X, then I assume that there's going to be a link prediction or link or relationship there, and if it's below, then I classify that as not having one. With machine learning tools, what people often do is they use those exact same measures, but then they feed them into a machine learning pipeline, like a random forest and some kind of classifier. What we did actually when we did our experiments for the book is we actually did some link prediction based on collaboration. So what we did is we took a citation data network, because if people are cited together on a paper, they worked together and they collaborated. And we used a subset of the data, and we used Neo4j to help create the features, and then we used Spark and MLlib to test and train our models. The workflow started, as you might expect, getting the information into Neo4j. We created a co-authorship graph. And then we, of course, did the typical explore, cleanse. We've identified some sparse areas like you would want to do. And then we did our feature engineering. And I'll show you a couple slides on some more specifics on that. Of course, then we needed to prepare for train and test splits, look at our samples. We did that in Spark. From there, we actually did our training. And I know this looks like a straight line from left to right, but it's not. You know, we had to do multiple iterations to make sure we were getting the results that we needed. But we trained in Spark, and then we evaluated our results, looking at things like the ROC curve and the area under the curve. We didn't productize anything, because that's not the business we're in. But that would be the typical flow. Now, as far as developing features, some of the graph algorithms, I'm just going to show you a couple because we use quite a few and we tested quite a few. For the link prediction, a lot of times those algorithms that fall under that category look at estimating the likelihood that nodes will have a relationship based on their proximity and based on the topology of the graph. We used just a couple of the ones we used with preferential attachment. That looks at the likelihood that nodes are going to connect based on multiplying how many relationships they already have with each other. Kind of sounds a little odd, but what it actually shows is a common network science concept of what they call preferential attachment. And you can think of that as the rich get richer, or people that are popular get more popular. And that basically recognizes that in most networks, if you have a large plane of existence, you have a large network, you're more likely going to bump into another node and acquire that in your relationships than somebody with a really small network. We also use common neighbors. That measures the number of possible triangles in the neighborhood. So that looks at what's called triadic closure, but that looks at how likely are your friends going to know each other. And the idea with that is really if there are two strangers with a lot of common friends, they're going to get introduced at some point. If you have a bunch of colleagues that are citing each other's papers, but you guys haven't worked yet together, you're more likely to work together in the future. So we found those two very predictive in the collaboration evaluation. Community detection, those are really, really common as well when you're trying to predict relationships in the future, basically trying to understand how things are partitioned and how densely they're partitioned. Triangle count and clustering coefficient were, in my mind, surprisingly predictive because they're basically looking at a particular node and trying to understand how many of those nodes' friends or connections they have in common. So how tight, how likely are your neighbors to already be connected? The other one we looked at, it was Louvain modularity. So that's basically helping to identify communities. You can think of it as a very scalable community detection. And it also looks at hierarchies of communities. So you can look at a large community that has a subcommunity, that has a subcommunity, that has a subcommunity, and you can dial in at what intermediate community you might want to use for your analysis. As far as training our model, we actually used a random forest as a binary classifier. This is just one decision tree in that forest. And just like you would use any kind of decision tree, we had some metrics. I think this is just common authors. You have some metrics, you had some thresholds, you make a decision, you go down one leg or the other of the path. And at the end, make an estimation of whether you're going to predict whether it's in the classification of has a link or doesn't have link. Now, I don't know if you guys have had this happen to you. This actually happened to us. We ran our model and oh my, the results were unbelievable. And you can probably, if you've done this, you know why. We were cheating. So the thing to be careful of is particular with graph data. If you're doing machine learning on graph data, graphs are all about networks and connections. It's really hard to randomly split your graph between train and test with connections because the data tends to leak over. You kind of cheat. You have tertiary information that's predictive left. So what we suggest in this case, and actually if you're doing machine learning on graph data, highly suggest that you split by time frame. So we picked a particular year. Everything before that year we use as a train, and everything after that year we use as a test. Just a very good way to get much cleaner breaks. As far as our results, this was our first model. Not too great. We've got true positive rates on the y-axis. We've got false positives on the x-axis. And the blue line is just your average random stuff. And then this is our first model that we trained on. Not that great. Definitely want to get that farther up in the corner there. And then after using multiple models and bringing that together, we were able to, in the last model, get our accuracy up significantly, as well as reduce those false positives and be more precise. So definitely playing around and tuning your parameters are very important. You'll go through an iteration cycle. One of the things to do when you iterate is to look at the feature influence when you're doing your tuning. So I mentioned the whole feature selection. Another thing to do is use the Spark random forest algorithm to take a look at the influence in each model of your different features. Far and to the left is P2 cited, so those are papers that are citing each other. If you're citing each other in the past, go figure, you're likely to cite and collaborate in the future. Not shocking, but that represents something that in another area, a domain expertise might be able to tell you. The other features are more graphy, if you will, or more related. We've got page rank. So if you're very influential in your network, you are potentially, it's very influential that, or it's very predictive that you may be collaborating with other people in the future. We looked at triangles. That was the density of connections of little groups. We also looked at partitions, so that's communities. You know, how are people in different communities? And if I were doing this professionally as a data scientist, I would look at this as well and maybe look at the things that were less predictive, maybe reduce those, see what happens to my model, and keep tuning parameters. So that is, I think, about all the time we have left for. But I think I have time for maybe one question at the end of this. Lots of resources. We have a code repository where you can get the data that we used from the book on the O'Reilly GitHub site. And then we also created a Python notebook as well for those of you who want to work in Python. If you're interested in this topic, download the book, whole chapter on it, lots of information. So in the back, do we have time for one question if anybody has it? Okay. All right, so if you do have a question, if you can come up to the mic. And it looks like we have no questions. So you guys feel free to find me downstairs as well. Thanks.